Hello, I am Nairanjana Dasgupta, commonly known as Jan, and I am a professor at Washington State University. And I would like to present my research on um, false positives, our power dependence. And I am really excited to present my work and get feedback from the group. Thanks. So my talk today is on large-scale testing, false positives, R power, and dependence. So the idea of large-scale testing and multiplicity has been in statistics and data science for a while. So what I'm going to do is essentially share an idea about a concept that we have been working on and sort of elicit some and solicit some feedback about some of these. Okay. So the idea of
Hey,
large,
Jan.
yeah.
I'm sorry. There's something up with your audio. It's like popping a lot. It wasn't doing that before. Are you using some kind of headphone or anything like that?
No, nothing.
Okay. Let's see if I can change something on my end.
I can start again, so no worries.
Yeah, I would start again. Thank you.
Okay, no worries. Okay. Today, I would like to share my research and ideas on large-scale testing, false positive, R power, and dependence. So the idea of large-scale testing and false positives has been in the statistical data science literature for a while. Today, the idea is to try and talk about R power, which is a concept we have been working on, and then see, what people think about it and get some ideas for some of the work we're doing on dependence in the presence of R power. So large-scale testing is essentially exactly what it sounds like. When we have on a single unit, we have many, many, many observations, and we are interested in comparing individuals or groups for a certain reason. Examples are, the most common example is probably genetic testing, like testing using microarrays, DNA microarrays, or genome-wide association studies, where we are comparing single nucleotide polymorphisms, or even image analysis. So fMRI is a pretty common application of the techniques that I'm talking about. So the idea here is that on a single individual, many, many, many observations, like for a single individual, many genes are collected at the same time. We are interested in comparing two groups, like cancer versus not cancer, disease versus not disease. And the idea is, if we are interested in comparing the two groups, we would do many tests at the same time, simultaneously. This would increase the probability of false positives, because in statistical testing, we always have the criteria of controlling for type 1 error. But when we do so many of them at the same time, type 1 error has a hard time being controlled. So there is, loads of literature on this, because this is not a new topic, especially since the genetic microarray literature and the genome-wide association studies have become common. But one of the things that I have seen when I have been working with practitioners is there is so much controversy about, do you essentially correct or try and figure out what the true type 1 error is, or do you not? I mean, what is the correct way of doing it? And there's a lot of controversy about it. So the technique that people use a lot these days is the idea of false discovery rates. But when I'm working with a lot of the practitioners, the people working on DNA microarrays and genome-wide association studies, I've noticed that most of the times people have a fixed amount of time and money to be able to follow up on the results of these tests. So the idea of R power came from this practical idea that even though maybe out of 26,000 genes, maybe 5,000 of them are quote unquote significant, we may not have time or money to be able to follow up on 5,000 of them. Pre-hoc, a lot of times we know how many we can follow up on. So what is the idea of R power is very simple. You go to the tests, and once you do the tests, you just rank your tests. You rank your, whatever outcome you have. You have a p-value, you have your test statistic, you just have your results, just rank them. And then pick your top R. R being decided by you ahead of time. You know you can only follow up on 100 genes through PCR, go for 100. Okay, so it is practitioner decided that how you pick this R. Then you just rank and go for it. So it's very practical, it's very easy to do. People sort of do it all the time anyway. But the problem was there wasn't really statistical theory to back this up in terms of how reliable is the list that you got. And that was the idea of R power. What is the probability that the list that you got is indeed the correct list, that it comes from the population of interest for us? So in 2016, myself and two of my colleagues published this paper in Sankhya, where we essentially found out analytically, how do you find how reliable my list is? Okay, so this, if you're trying to find R power, this is the way you compute it. It is, totally analytical and very much computable. It's just one integral, fairly easy to do. So it's not a huge problem in terms of a big data problem here, because a lot of the math makes the problem simple. However, this idea of R power was sort of estimated under two big assumptions. One of the assumptions was that all the units were independent of each other. If all the units are independent of each other, the integral basically becomes a unidimensional integral. But we know that in genetic studies, this is a very, very wrong assumption, because genes work in networks, genes work in clusters. We know fMRI as the pixels close to each other are highly correlated with each other. So now the current work that we are doing is trying to put in the concept of dependence in R power. So if I put in dependence, what happens? What will happen is this univariate normal density that I have becomes a multivariate normal density. And so here we would be integrating over the entire normal space. And if I am doing 500,000 tests, my integral would be of order 500,000. This is obviously a very, very difficult problem computationally and mathematically. So one of the things that we are looking at is looking at specific structures to try and make this problem a little bit easier. And then for the big data sort of idea, one of the other sort of avenues we are looking at is, can we use dimensionality of the data to simplify the problem? So even though we have 500,000 tests, maybe the true dimensionality of the data using eigenvalues, eigenvectors might be a lot less than 500,000. Can we use that and incorporate that in our test? I don't know if people are interested, and I am probably running out of time, but essentially, even though the formula looks kind of difficult out there, the math that is involved in here is, quote unquote, fairly simple. We are using conditional probabilities, we are using order statistics and different distributions to actually compute analytically what the process is. I will be happy to talk about, any ideas that you might have and some of the progresses that we have made in incorporating dependence, if people are interested. And I will essentially stop here and take questions. Thank you.